All right, so let's take a look at this circuit. I would like to cover a few things in terms of the transistor perspective and how to use a transistor and application-wise. So here the intended application is to turn on this lamp, but in order to turn on this lamp, that lamp requires at least of 12 volts. That's why my supply voltage on the collector side is 12 volts, right? But if I change this lamp voltage to like 6 volts, like you see maximum rated voltage, if I put like 6 volts, then I want to adjust this supply back to 6, otherwise I'm going to damage the lamp itself. So now let's say the lamp requires 6 volts. So I choose the collector side 6 volts as well. But from the base perspective, remember this is the base terminal. From the base perspective, how much voltage I have? 5 volts, which is more than enough. Remember that base requires only 0.7, but what I have is more than 0.7, which is I have 5 volts. So when I run this simulation, you see that the lamp was lit. The current drawn by the lamp is around 895 milliamps. So voltage on the base, as indicated before, it's 5 volts. But the problem with this circuit is you see current on the base is 11 amps going through the base like this. So it leaves positive, it goes through the base, come back from the emitter, is pretty much like this. So with 11 amps, you are going to easily damage the base region because it's a very lightly doped and it's a very thin region.
How come that 11 volts is more current on the base side?
Because the resistance is going to be extremely small of a closed switch. 0 volts. 0. On the emitter? That's a ground. You connect it to the ground, so you're going to read 0. See, the emitter was grounded in this circuit. So if you read voltage on the emitter, you will read 0 volts. But if you read current on the emitter, how much current you think it will be? Both currents together. That's exactly right, which will come in the next coming slides, because see, this base current is going like this, come back like this. So you see that on the emitter, the base current going this way. But on the collector as well, the current comes like this, goes like this. But collector side loop is this one. Emitter side loop is this one.
So the emitter is always on the bottom.
Emitter is wherever you see the arrow. I can flip this transistor around where the emitter can be on the top too. But wherever that arrow is, that's the emitter. When it is outside, it's an NPN.
So you said the collector flows current through the source, pretty much.
Yep, the collector current, right? It's decided by whatever you have on this side, right? To an extent where base current also have a capability to control it. But once you are beyond one point, there is no way you can control the collector current. It's on. It's like turning the faucet all the way high. That's the maximum you can go.
So what we call a base source, the base source. That's what we call it.
Call it what?
The voltage that's provided to the base.
It's a base emitter voltage. You require at least 0.7. The voltage between base in relation to the emitter, because that's the PN junction right there. PN junction requires at least 0.7 to overcome. So this circuit may not really work if you actually build it, because the current drawn is extremely high, like 11 amps. You can damage the transistor quite easily. For that reason, what we can do is, how can we lower the current? We're going to place a resistor right here. Now look at the voltage on the base. Is it going to be 5 volts anymore? So it's going to be whatever it is. In this case, the voltage on the base is 908 millivolts, which is 0.9 volts, which is higher than what we needed. Current is what? 4 milliamps, lot less than 11 amps. But the lamp still doesn't turn on because the minimum current that requires for the lamp is not 471 milliamps. So previous it was like 645, something like that.
If you apply that resistor on these, that affects the current going through the collector?
Yes, to an extent. Not all the way through, to an extent.
But how did they say that it has two different currents?
Again, that's what this shows. That's an explanation too, how that affects. So if you take a look at here, you have your base voltage, correct, which we call as VBE. So which is that 0.7 which is applied. So that 0.7 will gives us this current, right? Correct? See, this current right here is the current going through the base and the emitter, right? Can I control that current? I just showed you.
Or with the resistor?
So if I increase this voltage, obviously I put a resistor right there to protect it, but I can control it, correct? I can control that current. And next, so when the electrons, so now let's say you have this guy right here. These electrons, let me change the color probably to green. So now the base current is like this, where some of these electrons are going to the P region. Is it correct?
Right.
And then it's going back to the supply. So if I have this guy already, that's heavily positive, he's going to pull all these electrons because that's the positive side. And it's going to pull the electrons that are inside the P region as well.
Okay.
So that meaning that the current on the base can affect the current on the collector to an extent. That's what we call as amplification. Amplifier means you are increasing the current. You're going to have very small current. Observe the multi-sim circuit. Where is it? Observe the base current is how much only? Observe the collector current. It's 471 milliamps. That's what amplifier means. This is a current amplifier because I'm making the current larger. Correct? Small current on the base can control larger current on the collector side. That's the benefit of using a transistor. All you need is small current. 4 milliamps is not even needed, but it depends on the model number. Some transistors, remember the MOSFETs? For MOSFETs, all you require like 100 microamps, 50 microamps, extremely small, which better suits for digital applications like computers and all that stuff. That means if you have like 10 microamps here, you can still control the collector. But whatever you are doing on the collector, that collector supply decides it. Here I have a lamp of 6 volts, so I require a 6 volt source. Of course, I can put more than this. That eventually, if I leave it like this forever, I don't know, multisim shows a broken lamp, but usually it will burn the filament because the voltage is definitely higher than the rated voltage. I think I have maximum rated at 6 volts. Probably the power is not 10 watts yet. Yeah, power is only 891 milliwatts. So it's not enough power to. So let me put like 20. Yeah. So still the power is, you're still at 1 watt. So I changed it before. Let's say maximum rated is 1 watt only. I hope. Did I change it? Not change it? No. Let me put 0.5 maybe. Let me stop. So it should, yeah, I think it doesn't showing, but the current is not enough definitely to use it. But let me lower this to see. That's why usually base side for testing we put a potentiometer so that we don't need to replace these resistors every time. See that as soon as I lower it, you see the current was increased on the base perspective. Of course, the base current increases, collector current increases. The voltage on the base was increased slightly. We can do the math on finding out, which we will do at the end of this lecture eventually. But we can actually find out exactly what currents that the base is having and the collector is having, so does the emitter. But effectively, that's the base current direction. That's the base current direction. This is the collector current direction. Both currents will meet, and this is the emitter current. That's why this arrow is pointing out. That's basically implying that this current coming from the collector to the emitter, conventional direction, positive from the source to the negative. But 0.7 volts on the base is a must requirement to have if you have a device. So loads will be whatever the load is. If it is a motor, a lamp, a speaker, whatever the load is, the load will always going to be on the collector side when you're using the transistor.
So the collector is negative feed, usually like negative 5, negative.
It's an NPN. That's the doping. N-type, P-type. Yeah. You can call as like N positive. Sorry, N as a negative. It's possible to call like that. So you're going to see subsequently now some circuits that shows you the operation again. So this one is, you look at the base voltage is only 0.6. Observe the base current is like 0.77 microamps, but the collector current is like 80 microamps, correct? Yeah, base reading 0.6 volts with a current of 0.77 micro, but the collector is at 80 micro. Is it true? If you move the decimal 3 places to the right, so that's basically 80 microamps, right? So if I raise the voltage, you look at the base voltage was raised to 0.7, which will subsequently increases the base current. Now the base current was 24 microamps. The first one is 0.77 micro. But now look at the collector current, which is, so as soon as, previously it was 80 microamps, but as soon as you hit that threshold required from the base perspective, the collector current was increased. Yeah. So you see that this one is fixed. We can leave that fixed. What? Oh, the 0.61. Yeah. Ideally, that's usually, but when you real practical way, when you get close enough, it will be on. And the next one is when you raise to 0.8. Previously, it was 24 or 7 milli, I think, something like that. Now you are at 608 micro now. And the current was like 70 milli. So as you can see that increasing the base current will increase the collector current to an extent. But beyond that, because remember always, collector current is decided by who? The supply on the collector side. So this is what happens. If you increase the base current, the collector current increases, and you reach a point where that increasing no more happens unless you increase this supply. Yeah, because collector side maximum current is decided by whatever the supply you choose. It's like that same faucet example with the water. If the faucet is completely off, that means the transistor is not on. So if you increase the faucet, the tap itself, that means you are increasing the base current. That means you will have more flow of water, correct? But if the faucet is all the way up, that's the maximum you can go, right? So that's the maximum current you will get from the collector side. Yeah. Yeah. Yeah.
So that's what it's saying about this is turns
Yeah. As the base current increases, we usually called as IB, an indication for base current. When base current increases, the collector current will increases until you reach to a point where it's not going to increase anymore further unless you raise your supply on the collector.
At that point, what's that point?
We haven't talked about that point yet. So there are some terminologies which will be coming in the next class, but it's called as saturation. If you're wondering what it is called as. One is on the base side, one is on the collector side. Base is this way. Yeah. Base current is the current actually on the base. So this is another, if you keep on raising, the same thing will happen. So now this shows you the previous relation. I think this formula also you will see. I want you to keep holding that formula sheet, flip the back side of it. You will see some formulas. You probably will see this one too. Emitter current is combination of collector current. Remember that collector current goes this way and base current goes this way. So in here, the base current is like 12 milliamps. The collector current is 461 milliamps, but the emitter current is. So which terminal in a transistor will always see the highest current? The emitter. Emitter always sees the highest current in a transistor because it's a combination of base and collector, but usually it will be very close to the collector, because base current is going to be extremely small always. Does that make sense? Base current should be very small. That's why collector current and emitter current are usually very close. But this shows you, like, you have 12 milliamps, you have 461. If you add those two, you pretty much get 473.
I have a question for you.
Yeah.
So if that arrow would be emitter, if that arrow was turned the other way,
Wherever you see an arrow, that's it.
but if the emitter was turned,
If the arrow is inward, that means it's a PNP type of transistor. It's a different type of transistor.
we haven't talked about now.
PNP you're rarely going to see in this course. But the usage of some PNPs, their operation is exactly identical, except you require negative polarities wherever you see. You all require, it's a negative. You flip this source if you use a PNP. You flip this source if you use a PNP. So that's why we don't usually talk about PNP, because everything is exactly identical. Even there too, emitter is the highest current seeking terminal. So
once the base gets to 0.7, you get 0.7 volts and the voltage from the collector.
again, that 0.7 is only going to be on the base in relation to the emitter. Collector side, you may get something different. See, there are two loops here, correct? One loop is on the base side. One loop is on the collector side. The voltages might be different. They're not going to be the same. But we will do some calculations to talk about exactly, and then we will relate to some applications too, what really happens in the next class. But today is just an introduction to some of the basic things. All right, so that being said, the emitter current is combination of collector and base. Emitter sees the highest current. After that, the collector sees the highest current. The least current is the base. That's the advantage. All you need to provide is extremely small current to the base. You can control large currents on the collector side. So I can give you lots of examples on why, because there are some circuits. For example, I have a circuit. Let's say this circuit X can provide a maximum current of not more than 1 milliamp. That's the highest current that you can draw off of that circuit. If you do anything higher than that, that circuit will damage. Right? That's the circuit X. And you don't have control over on that circuit. So this is like processors. Does you guys know like an Arduino on those stuff, like Arduino processor, Raspberry Pi like that for robotics? So those processors, there is a limit on how much current you can draw from those processors per pin. So let's say this circuit, you can draw a maximum of 1 milliamp. That's it. But let's say you have a fan, like your CPU fan, for example. But this fan may take 180 milliamps to even start running. Right? Now, my application is, I want to run this fan using this processor. What can I do? Can I connect them directly? So what can I do is, I take this processor, send it to maybe a resistor if I need one, and I put it to the base of a transistor, whereas this fan is going to be on the collector with its own supply, and you're going to come back, basically meet on the emitter. This is the application perspective where you will see something like this. And it's always going to be like that. Wherever you see like your, for example, displays turning on and off, your CPU fan, for example, in this case as well, the lamps, if they're being controlled automatically, you're going to always have a very small current that is coming down, but you can control the huge currents on the other side. That's the benefit of having a transistor. So now there are some terminologies we should be looking into. From the previous circuits, we saw that collector current is higher than base current, correct? So how can we, who decides that? Like, so if I want to calculate the collector current, remember collector current is indicated by IC, C for collector, and IB for base, IE for emitter. So is there any relation that I can find this collector current if I know the base current? So, yeah, if I don't know the emitter current. Let's say, for example, if I know, so who decides this current? in transistors, there is something called as beta DC. So that symbol is called as a beta. And so that's like that. So beta DC, that means it's talking about only DC currents in here. So beta DC is, what is beta DC is? It's a DC current gain. What is this gain means? Gain means, for example, this is from the amplifier standpoint. So for example, if I go to this application where I have 12 milliamps here, but the collector current is 461 milliamps, correct? So how much current am I gaining? And of course, yeah, so you can subtract it, you can tell how much current you are gaining, correct? So, but gain, if you are giving in, let's say 12 milliamps to a circuit, and if you're reading 461 milliamps, if you take the ratio of these two, meaning how much that came out to? Yeah, 461 divided by 461 milli divided by 12 milli. 47, you said? 38.41. So what does that mean is, this circuit, whatever this circuit has a gain of how much? So meaning that the input current will be amplified by how many times? 38.41 times, then you will get your output current. So the term gain implies it's a ratio of output divided by the input. So for example, I have an amplifier, let's say I have 1 volt and I have a gain of 20. How much I'm going to get out? Current gain. So the gain is basically the output voltage here is whatever the input times the. So if I have 1 volt, if a circuit has a gain of 20, then the resultant output would be 20 volts. So gain is a ratio of output divided by the input. So exactly that is what this beta DC right here is, which is usually given by the manufacturer. Of course, we can calculate by performing a lab on it. I think there is one lab that we will be doing on the transistors. Probably not today. So this beta DC is a ratio of what? It's the collector current divided by the base current. All right, so let's continue with this. So that's what a beta DC implying that it's a ratio of collector current to the base current that will provide us the gain of how much current that we are gaining. Gain, when you see the term gain, is always a ratio between two values, whether it's a current ratio, voltage ratio. In this case, it's referred as a current gain because it's a ratio between the currents itself. So that's what the beta DC is. Beta, it's a ratio. It's only DC, so there is no AC involved when we refer to the beta DC. It's IC over IB. Of course, you can rearrange it to calculate whatever the values needed. So let me give you a couple of examples. For what? So alpha DC, it's actually the ratio between collector to the emitter. So this alpha DC, it's a ratio between, you see that this is collector current, beta DC is collector current to the base, but alpha DC is collector current to the emitter. So which one is higher? Does collector current is higher, emitter current is higher? Emitter is higher. That's why alpha DC is always going to be less than 1, because the denominator is always going to be larger. And beta DC is usually in the order of 50, 60, 70, 100, 200. Depends on what type of transistor and the manufacturer. On the data sheet, it's usually referred as HFE parameter. But we don't really talk about that in this course. But it's called as an HFE value. So that's an indication. Yes, alpha DC is always going to be less than 1, since the denominator is always going to be larger. But for beta DC, it's more than 1 always, because collector current is always larger than base current. Base current is usually the small current. So, all right, so let me give you a couple of examples.